There is a problem with Ampere's law. And Maxwell, since we're talking about electromagnetic waves, that's our topic, the next 2 weeks, EM waves are scheduled for this week, Maxwell's equations scheduled for next week. They're all going to bleed together because it's the same thing. Okay? So we'll really be on the same topic. I'll probably change the folder to be a 2-week folder. We'll see, or just part 2. But they're all the same when it comes down to it. So let's So Ampere's law, as we've said a few times by now, that when you have current flowing through a wire, so that's what I is referring to in the right-hand side, that the product of that current enclosed by the loop that you're adding up over here on the left-hand side with the fundamental constant related to magnetic fields means that I can add up all the magnetic field pieces along the path. But what path am I talking about? So this is a path integral, so it's a loop. Actually, by loop, it also could be an area, a surface area. Okay? So here's a WAR. Okay? So we have this wire, and if I put a circular loop around that wire, then I'll be able to, and just go back to the movie, that's why I love that movie, I keep referring back to something that's more entertaining than a lecture. All right? What did they notice? You run current through a wire, magnets that are right angles to the wire start wiggling. Why is that? Well, now we know magnetic fields are zooming out of that wire. They're radiating outward in circular patterns, concentric circles to this one. And so that means magnetic field going through this thing. In fact, right-hand rule for this kind of thing, curl your hitchhiker's thing, your thumb's the direction of current flow, the curl of your finger is the direction of the magnetic field. So that magnetic field's looping, going around a circular loop. So the simplest version of this is the circular loop. That's the surface that this path integral is working on. Okay? However, I could have any surface. So if I wanted to, I could have this thing, it could have this, if that circle could somehow stretch out into a sock. Okay? It doesn't matter. That'll just change what L means in the integral. That's all. It makes it geometrically harder, but it's just geometry. Okay? So that's great. We know that now, but what if I'm dealing with a capacitor? So what if the surface contains a capacitor? Okay, well let's, I'm going to go to a new screen, so I got space. So let's see here, I'm going to, here's a capacitor plate, that's a lousy capacitor plate. another one. And so let's have a wire, and we'll come up here to a battery. And so this will be our wire, all right, connected to a battery. And so let us, and we'll assume that current is flowing as such. So if I do my loop again, my so I'll call this loop 1 in our BDL business. Clearly, at that loop, the current enclosed is the conduction current in the conductor, really referring to moving free electrons. All right? If I extend that a little bit, stretch that circle out into a sock, if you will, okay? I still have, I'll call this loop 2, surface 2. I still have current enclosed. However, if I change the surface 3 here, now current's 0 because there's no current between the capacitor plates. There's no current there. And if I take it out to here, well, then I get current back. So in situations 1, 2, and 4, I enclosed by the surface equals the conventional current, but in situation 3, I enclosed equals 0. And this is where Maxwell comes to Ampere's rescue by creating a thing called displacement current. Okay? And displacement current kind of sneaks through the back door by means of electric flux across the plates to define a current, quote unquote. All right? And this is essential because electromagnetic waves don't involve a conductor. Electromagnetic waves are traveling through free space. There's no wire. Okay? Yet we're getting magnetic fields inducing electric fields, which induce magnetic fields, which in turn induce, they keep inducing one another in that regard. So the original form of Ampere's law was ambiguous, but Ampere was long before Maxwell. He just didn't know. So his law was perfectly legit if you're dealing with a conductor. Okay? Not a break in the circuit, that it was what a capacitor is. Okay? Now, remember with capacitors, what happens? You do get current flow because immediately electrons start leaving one of the plates, going through the battery and piling up on the other one, which makes one of the plates more positive than the other, and thus you have an electric field across those plates. And so you do get current flow in a capacitive circuit, but not through the capacitor, at least not in a conventional way. Okay, so we have conventional current, and then displacement current would be unconventional, very unconventional current. All right, so what we're getting at. So I think I'm going to have to redraw this just so that I don't get these ideas confused. So if we have a battery connected to a capacitor, well, what we're going to get, so if, let's say conventional current is flowing this way, and so this is a dq per dt kind of thing. We're dealing with an area on these capacitor plates. There is an electric field, a uniform electric field, extending from the plus plate to the minus plate. Has to be that way given that current's flowing this way. Conventional current is in the direction of the electric field, vice versa. And we know that the electric field is proportional to charge per unit area for a capacitor. And in fact, it is Q per epsilon naught area. We have the fact that the electric flux, these are things we've done a while back, is flux is always whatever field is providing the flux times the area that that flux is going through. It always works out that way. All right. And so what do we get? And we did this a while back when we were dealing with capacitors. The electric flux ends up being, if I plug, basically I'm going to multiply this thing up here by A, which means I just have Q per epsilon naught is our electric flux. Okay? So the question that we're aiming at answering here, what does, I equals dq per dt, the time rate of change of charge flow, mean with respect to a capacitor? Okay? That's really what we're setting our sights on in this lecture. And so I would say one, well, I'm going to type this out, be clear. For one, charge on the plates is clearly related to the electric flux. So just make sure that that's as obvious as it seems to me. The electric flux and the charge are related to one another because as this transient unfolds, more and more charge piles up on either side of this capacitor. As negative charges leave the side that's becoming more positive, the same number of negative charges are piling up on the other plate that's getting more negative. And so the amount of electric flux keeps increasing. There's more electric field lines because there's more plus to minus connections in the field. Okay? So they're clearly related. Okay? How they're related? We'll get to that, but this is just kind of thinking it through. And the time rate of change of charge is related to the time rate of change of the flux. So this thing, displacement current, Maxwell's contribution. He writes it as an I sub d for displacement current, and it's defined as the time rate of change of the electric flux. And hopefully it's becoming more and more sensible that if it's electric flux, it's going to have the electric permittivity constant. If it's a magnetic flux, it'll have the magnetic permeability, et cetera, et cetera. All right? So this situation now, Ampere's law, if it had this additional term in it, if current was the enclosed current, which has up until this point been only the conventional, or what you might call the conduction current, and it's a conduction current because it deals with a conductor, but the space between a capacitor is never a conductor unless you've ruined it. If you over voltage it, then it'll break it down, and then the insulator finds a conducting path. All right? So we have this new term to add to Ampere's law. So the Maxwell Ampere law goes like this. Starts off the same as Ampere gave it. So for some loop, the sum of all of the magnetic fields along the loop will be the magnetic permeability constant, and now it's going to be regular conventional current plus this displacement current. And so what this boils down to is mu naught I, like we saw before, plus mu naught times the epsilon naught electric flux change per unit time. So the Maxwell Ampere law, same as before, but now we have this extra term. So this applies for all the possibilities with electromagnetic waves. If you're dealing with a conductive path, then you have both. If you're not dealing with a conductive path, then you only have Maxwell's contribution. You only have displacement current. But realize it's different. It's accounting for current in terms of its association with electric flux, which is a parameter of the time rate of change of conduction current, at least in the circuit we looked at. But with an electromagnetic wave, you only have displacement current. You don't have a conduction current. And we're studying electromagnetic waves. We're beginning to. All right? So that's the Maxwell Ampere law. So we could say, this is the conduction current, displacement current. All right. And we could, I guess in English, we could write a magnetic field is induced by a changing electric flux or by a current. So this is what we're going to be dealing with EM waves. So this is the fourth of Maxwell's equations. The first two equations are Gauss's law for electric field and Gauss's law for magnetic fields. We did that a while back. Okay? And then Faraday's law is Maxwell equation number 3, and the Maxwell-Ampere law is Maxwell equation number 4. Okay? And you might have seen it. There's T-shirts and coffee mugs. And it has the 4 Maxwell equations, and it said, and God said, let there be light. And here's Maxwell's equations, which all light is an electromagnetic wave. All electromagnetic waves move at the speed of light is what we're going to work on next. Okay? So we have some math to do, following in Maxwell's footsteps, to show that to be the case.